Okay, so we're waiting on people to trickle in from the lunch. I'll get started with a couple of the administrative things. On the website, on the left side, there's a resources area now, and there are lots of things in there. There's links to books, a lot of them that you can get from the library, YouTube channels, helpful websites, mechanical and electrical parts suppliers. There's lots of things on there. So if you haven't looked at that section of the website in a while, probably finished it last week, have a poke around there and see what all's new. The pressure vessel activity, if I had it when I got on the plane, you should have it back. Other than that, I haven't had a chance to grade them, and I was going to grade everybody else's in one batch. So expect that probably Thursday if you don't have it. A couple things that were common on there. The Young's modulus, where we asked for 6061 T4 aluminum, I think. If you go on the link that provided, there actually was a Young's modulus listed for the material. Some people ended up calculating it, and it was close, but it was a little bit different. Just make sure you really thoroughly look through those data sheets. I didn't count off for that. And there was a typo when you're calculating the flexural rigidity of the plates on the end of the pressure vessel. On the website, there is a 1 minus nu, and it should be 1 minus nu squared. That was my fault that it was a typo. Luckily, it impacted your answers almost none. So I obviously didn't count off for it, but FYI, if you are going to design a pressure vessel and need it to not blow up because you're going to be in the room, make sure you use the updated version of that equation that's right. The thing that most people missed was calculating what size of bolt to use. And if we need to, we can go over that maybe Thursday once I've made sure I've got everybody's graded. Basically what you need to do is calculate how much total force is acting on the plate. Some people just took the pressure and divided the pressure by 6 or 8 bolts and said that was it. But you actually need to calculate, the pressure inside, and you know the area of the plate that's exposed to the gas. And so if you calculate how much force is on that plate, it's about 17.5 tons. And so some people that did it incorrectly got a very, they said that you could use 6 number 8 screws to hold it on. And those are pretty small screws, so there's no way that's going to hold 17 tons of force. So make sure you kind of think through, have that BS check going in the back of your mind the whole time of, have you ever seen a pressure vessel with really small screws holding the lid on? Probably not. Are there any questions from that homework that we didn't talk about already? Everybody overall did pretty well. I think the average grade was somewhere in mid-B range, so not bad at all. But before we go through today's lecture on transducers, we're going to take 10 minutes, so go ahead and close your laptops, and we're going to do a little quiz that goes over some stuff from what we've learned from the first of the year until now. So it's not a ton of points, but it's just to see if, make sure that encourage you to go back and look over some of the material and try to internalize what we've been doing. So we're going to take 10 minutes to do this. The image is a little fuzzy on your copy, so there's the image. Okay, so what we're going to do today is talk about transducers. And then on Thursday, we're going to talk very briefly about calibrations. We may finish this if we don't get through it all today. Depends on how things go with our late start. And then on next Tuesday, we're going to do some strain gauge stuff. We'll talk about that at the end. But we'll be doing activities for the next couple periods after this. So it should be less slides and more doing some hands-on stuff. So transducers are the way that we talk to the world. We talked about this earlier in the data acquisition lecture, which was way, way, way back. And the idea is a transducer, just by its definition, could be we're getting input from the world or we're putting some kind of output out into the world. There's some argument over transducers and sensors and the exact terminology. But you'll see a lot of these words like active, passive, transducers, actuators, generally something that affects some physical change in the world, and bidirectional transducer. And if somebody uses active or passive transducer, you should make them clarify what they mean, because they mean different things to different people. In some cases, an active transducer would be we're sending some kind of a signal into whatever we're trying to measure. So we're It's like active source seismic sort of. And passive would be we're just listening to the system. From an engineering standpoint, generally when we mean an active transducer, it means we have to put energy into the transducer. So we have to hook it up to some power source and excite it. And a passive transducer is something that just sits there and we can get something directly out of, like a thermocouple, say. And bidirectional transducers are transducers that can either be a sensor or an actuator. So think of like a piezoelectric element. If we strain that piezoelectric element, it will generate some voltage. We can use that as a passive transducer, or we can apply a voltage to it and it will generate strain. That's how buzzers, piezo buzzers work and that kind of thing. A speaker would be another example. A speaker can generate sound waves from electric current, these pressure waves, or it can take pressure waves and turn them into electric current, which is what the microphone's doing right now. Okay, so when you're looking at transducers online, you're going to probably see these words or some variation of these words describing the performance and the characteristics of that transducer. I know there's a lot up there, but we're going to go through them. It's just going to be like one slide for each word, because when you break them down into each element, they're not too complex, but you need to make sure you understand them so you get the right transducer for the right job. There's nothing worse than spending $700 or $1,500 on a transducer and finding out it's not actually the one you needed to do the task. The first one, and the thing that actually will cut most transducers out of the running, is what range you need. So this is from a manufacturer of proximity and distance sensors on their website. And here they have a range row on this that tells you over what range this transducer will work, what it can sense. So here, 100 to 200 microns displacement, or here 10 microns to 12.5 millimeters displacement. So if you need something that measures meters of displacement, maybe this isn't the one for you. If you need just a few hundred microns, you could go over here. Up here, 50 microns to 12.5 millimeters would be one of the larger ranges that they offer. So range is a pretty simple concept. You can think of it maybe for a load cell as well. A 0 to 2,000 pound force load cell, well, that's the range over which you can use it. If you use it above that, you're probably going to damage it. The linearity of a transducer, an ideal transducer would be perfectly linear. If you say you double the input, the output would double. So ideally, input to output would look like this. Say it's a displacement transducer. We move it 1 millimeter, then we move it another millimeter. We'd expect to see the same step each time in the output voltage. Very few transducers are linear, strictly. A lot of times they're very nonlinear at the ends of their range, especially the center of the range is the most linear. But this would be a really nasty nonlinear transducer. So in that case, you could either find a different or a better transducer or do a more complicated calibration and data reduction routine. But ideally, you want a nice linear transducer. Most of them are, the linearity is generally specified as a percentage of full scale within a certain range. So for the center, 80% of the useful range of the transducer, maybe a 0.5% full scale nonlinearity would be a pretty typical spec for something. Linearity also can be a function of other things. If you're doing experiments that go to very high temperatures, this would be in the data sheet of the transducer probably, or you might have to ask the manufacturer if they've tested for how much the linearity varies as a function of temperature. Could be a problem for you. Changing other things along with what you're trying to measure can always introduce complications when you're trying to use a transducer. The next one is the sensitivity of the transducer. And we're going to talk about calibration, like I said, on Thursday, but this is a graph of input. So let's say where we are in space on a displacement transducer, or where we are in force on a load cell, and the output voltage. And if we're doing this calibration, we get these data points. And then the slope of the best fit line to those is the sensitivity of the transducer. So how many millimeters per volt or how many kilonewtons per volt does the transducer produce? So if you need a very high sensitivity, then you've got to look for that in the spec. Higher sensitivity generally means lower range as well. It's a trade-off that you always have to deal with. Another one, and one that gets left out of consideration a lot, I find, is the response time of the transducer. There is no such thing as a transducer that instantly responds to a change in the system. So you're going to have something. If it's a mechanical sensor, maybe you've got some inertia going on. You've got some inertial effects. If it's a temperature sensor, and I have my temperature sensor and I stick it on a hot plate, it's not going to instantly jump to the temperature of the hot plate. It's got some thermal mass that we have to overcome. So if we have a step function that we put into a transducer, say that I pull the rod out and push the rod back in, or that I put the temperature sensor on a hot plate, there's going to be some kind of response time where the transducer is going to smooth out what we're measuring a little bit. It's specified differently for pretty much every manufacturer and every transducer. Some people do, it takes this long to get to 100%. Some people do this 10 to 90% response time. You just have to look, and it makes comparing transducers very hard because you generally have to convert all the manufacturer's units to one standard unit when you're doing your comparisons. Same with linearity, really. Does response time make sense to everybody? Takes a little while to see effect. Okay. The stability of a transducer is another one that's big, and for shorter lab experiments, this maybe isn't as much of a concern for one experiment, but between many experiments possibly. If you're having a field deployment, so you put a pressure sensor out somewhere in the ocean, you want to know that that transducer is going to be stable over months to years, that you're not going to have lots of long-term drift in what its calibration is or what its zero is. So maybe you've got this nice original calibration. So this will be the black line would be the ideal. This black curve, let's say this transducer is a little bit nonlinear. And then 6 months later, maybe that calibration curve has moved a little bit. In this case, 0.1% of full scale. But that's something that if you've got a sensor that's out for a very long time, you want to be mindful of. In the lab, we try to calibrate things, have in the past anyway, try to calibrate semi-annually, which is a pretty standard, semi-annually to annually is a relatively standard calibration cycle for a lot of transducers. But if you have something in the field, say a seismometer, you may not be able to get to it very often. And then the precision and the accuracy, I don't think I need to go through the analogy about the difference between precision and accuracy. Hopefully everybody is familiar with that. If you're not, definitely go look it up or ask questions or say right now, do we need to go through precision and accuracy, or is everybody comfortable with the difference? Okay. So make sure that you look at these specs for the transducers, how reproducible the measurement is, and how close it's going to be to the actual physical value that you're trying to measure. A lot of times we don't necessarily care how close it is to the actual physical value. Maybe we want just relative changes. We really care about how precise it is, maybe not how accurate it is. It depends on the situation and what you're doing. Another one, and there is no rating for this, the IP rating system that we talked about back when we talked about sealing, maybe you could say is a durability rating. But transducers get exposed to all kinds of environments. This was a pressure transducer, and it was used in salt water, and it had something called a ground loop that maybe we'll get to talk about. Basically, there was some current flowing through the housing, and the housing of this transducer completely dissolved in the water. It wasn't rated for these kind of conditions. So you want to make sure that your transducer is rated for being submerged in water, being in corrosive substances, being in a high pressure environment or a vacuum environment. Otherwise, you end up with very bad things happening to your transducer generally. Another thing to consider, again, you won't see this on the data sheet, but is the signal conditioning. This is going to impact the cost to use this transducer. So say we're looking at using thermistors, which we're going to talk about, to measure temperature. The actual sensor itself is very cheap. It's much cheaper than something like an RTD, but the signal conditioning for it is going to be more expensive. So you have to do this trade-off analysis of how many of these sensors am I going to use? Does it pay to buy a couple that have all this stuff integrated into them, or do I buy lots and lots of sensors and some expensive signal conditioning hardware to go with them? Also see the offset is generally stated, again, some percentage of full scale, a lot of time, which is just a DC bias or a zero offset. So if you have a pressure transducer and you have no differential pressure on it, what is the maximum differential pressure that it's going to tell you there is? So what's that DC offset from what there should be? So you can see it would shift this ideal curve. It could be a function of temperature. It could be a function of lots of things. Another one, those that were in the lab meeting this morning for our group, we actually talked a little bit about hysteresis, but it applies to transducers as well. If you have a transducer, say we have a load cell or displacement transducer, and we go up in load or up in displacement, and then we go back in the other direction, you want it to tell you the same thing both times, ideally, right? But some transducers do have this hysteresis loop where on load up and on unload, you could get different answers. And that's something you'd have to consider in your calibration. Most of the time, the hysteresis is very small for a good transducer. You could sort of think of it in backlash, as a backlash of a machine, if you want to think of it in machining terms. Another one that gets considered less than it probably should is the dynamic linearity of the sensor. Think of it as trying to figure out what the transfer function of the sensor is. How does the sensor's response change as a function of frequency? So if you've got a DC-DT, it has a limit to how fast it can respond. So again, getting to response time. And you're going to get some kind of funky transfer function where maybe very low frequencies for this sensor, you get this high pass effect. Then you have this usable region. And out here, maybe your sensor hits some kind of resonance. And that data would also be not valid unless you take this into account. This one's really tricky to pin manufacturers down on because a lot of times they haven't done this test for different kinds of sensors. For example, try to find a dynamic linearity curve for a load cell. It pretty much doesn't exist. So you might have to do that yourself or beg them to do one for you. So that's, I think they've just normalized it here, but you could think of it as if this were 1 being the true divided by what we get, then if you're down here, maybe you get this high pass effect, so you measure less than what is actually taking place. And out here, when the sensor is resonating, you would measure more displacement than there is, let's say, or more load. That makes sense to everybody? Yeah? It's like I said, think of it like a transfer function. Maybe when you're doing a seismometer instrument response correction, think of it kind of like that. Okay, so now I'm going to show you some of the basic sensors that we use. Temperature is by far the largest section of this because sensing temperature is tricky. There are a lot of ways to do it, and it seems to be one of the more challenging. Strain gauges is the other big section. Okay, so got to change the title on that, but we're going to talk about thermocouples, RTDs, resistance thermal devices, or resistance thermometer devices, and thermistors. Each of these have a different set of trade-offs that you can get. So for example, if we're looking at the temperature voltage output for a thermocouple, you can see we've got a pretty nonlinear response. Temperature resistance for RTDs and for thermistors are also nonlinear. You can think of the slope of that as kind of the sensitivity. So these are going to have different sensitivities as well, and then they have different costs associated with each of them. Okay, so that's all of them laid over each other, if you want to see. So a thermistor is generally considered very sensitive. RTDs are relatively sensitive. Thermocouples are pretty coarse instruments, but something that we still use because they're cheap. So we'll start with thermocouples. Has anybody heard of the Seebeck effect? Vaguely? Okay. This is something that if we had more time, I'd do a demonstration, but you can do it for yourself. If you go up into the lab, take a multimeter, set it on millivolts, or you could even set it on a low current range. Connect the two ends of the meter together with a wire, and then hold one end. And if you have a temperature difference across this wire, it will generate a voltage. We're not going to go into the physics of why that happens. It's all on Wikipedia if you're interested. But the idea is we can actually use the same metal or different metals and create a temperature sensor, which is what's called a thermocouple. And there are lots of different thermocouple combinations out there. Alumel, chromel, copper, they have all these different alloys that they use. But the idea is you have two dissimilar metals that go down and they're joined at the end, and that is going to be where you're sensing the temperature. As we change the temperature here, the voltage output of that thermocouple will change. Unfortunately, it's in a pretty nonlinear way, but they're very, very well characterized. So these are some of the different thermocouples that are out there. There's lots, but J, K, E, and T thermocouples are some of the more common. K has a very wide temperature range, so -200 to 1250 C. But you can see So in the best case, the limits of error are 1.1C or 0.4%. Standard, so 2.2C. So maybe not super great, but they're cheap. For smaller ranges like a T-type, you can get down to ½ degree C or so. And the only difference between those is the different kinds of metals that are used in them. But the challenge is, remember, any two kinds of metal that we have joined together are going to be a thermocouple. So let's say out here, you have your thermocouple on your experiment, and this would be a type K. So we've got chromel and alumel alloys, the wires running back. And then we're going to connect it to the computer or to our multimeter, whatever. Well, now we have a chromel copper and an alumel copper junction. So now this circuit has 3 thermocouples in it. And these two are going to change with the room temperature. So that's not an ideal thing, right? We want to be able to correct that out. And there is a way to do that. When they calibrate these, see, do we have a picture? Yeah. When they calibrate these, they actually put those junctions, they're called the reference junctions, in a bath of ice water, so we know they're exactly at 0 degrees Celsius, and then calibrate the thermocouple, and that's where we get these standard tables of how many millivolts out per a certain temperature. Then now in software, if we measure the temperature of the room that we're doing this in, we can correct for those. It's called a cold junction correction, cold junction compensation. This is a really bad source of error for people when they don't correct for that, because then the temperature that you think you're measuring is a combination of your experiment and the room temperature, which in this building is a very bad thing, because our building temperature varies all over the place. So NIST, the National Institute of Standards, does this experiment for every thermocouple over its range, and they produce these tables. This is a section of one table. You can get them online. You can get them implemented in all kinds of programming languages. So here we're starting at negative 270C up to 0C, and then these are the increment of that. So 0, -1, -2, -3, and so on, and then -10, -11, -12. That is the output in millivolts of a type K thermocouple for that temperature. And it's very, very reproducible. So by using this table, we can back convert the millivolt that we measure to an actual temperature. The other way, and this is probably the most common way, because storing those tables in your computer, especially if it's on a small microcontroller, takes a ton of memory. I don't think you could store the entire table on your Arduino, actually, just a subset of it. We use these high-order polynomials. Again, on the NIST website, you can get the form of the polynomial and all of these coefficients. And again, try to find a library that has all of those typed. I've had to build the Python library at one point for doing this, and trying to type all of those numbers with no typos takes a long time. So any questions on thermocouples, how they work, why we do cold junction compensation? When you're looking for a thermocouple signal processing unit, a lot of times you'll see that they say they have an isothermal block, which means that right here, where you attach the thermocouple to your National Instruments card or whatever, it's a very thermally conductive massive material, so that these two junctions are at the same temperature and are at room temperature, so your cold junction correction works well. And so if you take it apart on the circuit board, you'll see these big areas of copper and big, huge metal studs that they're doing to try to keep everything the same. The RTDs are another way to measure temperature. These are more expensive than thermocouples and more expensive than thermistors, but they're really pretty nice setups. You can buy them from Omega Engineering. The idea is the resistance of this changes based on whatever temperature it's at. So you have to integrate this into some kind of resistance sensing network, you know, a full Wheatstone bridge or a voltage divider or quarter bridge, however you want to do it. And they look pretty similar to thermocouples from the outside. It's just a metal sheath and the sensing element down in the end. But this is where you can get bitten by the cost of doing the signal processing if you're not careful. Thermocouples, the signal processing is relatively straightforward and relatively cheap because everybody makes something. Here you are having to either have a voltage divider or some kind of bridge. So this would be the simplest setup, where we have a Wheatstone Bridge, so those 4 resistors are RTDs out here, and we're measuring the bridge voltage here. So you would need to have 3 precision resistors to make this work, so 3 0.1% or better resistors. Not horribly expensive. But you can still get in trouble because of, if these wires are long, the lead resistance is significant and can throw you off. So you get around that, now all of a sudden you're running a 3rd wire back to measure the voltage across the bridge. So now you're running more wires, more places for interference to get in, more places for things to break. Another way to do it is to use some kind of a constant current source and measure the voltage drop across the RTD, and then from Ohm's law, you can go ahead and get what the resistance is. Very related, thermistors. These use a different mechanism to change their resistance with temperature, but you treat them pretty much the same. There are so-called Ptc and Ntc, or positive temperature coefficient and negative temperature coefficient thermistors. So negative temperature coefficient would be the hotter you heat it, the resistance decreases. Positive would be the opposite of that. These are really cheap. Something like this, it's just this little glob on the end of a wire, might be 50 or 90 cents from DigiKey. But then again, you have to do all the wiring right and have a balanced bridge to really use it. You can do this with your Arduino. In fact, this is a pretty easy assembly to build. You just get some cable from the hardware store, get your thermocouple, solder it on, maybe heat shrink some tubing around it to make it look nice. You could buy this as is from Adafruit for $5 or $10, or you can buy the wire at the hardware store for about $1 and buy the sensor for $1 or less and do this yourself in 10 minutes. Save a little bit of money. But here they've got it set up as a resistor divider, right? So we have a changing resistance and a fixed resistance. And you can see how we can compute the resistance of the thermistor. Now to get that to a temperature, remember thermistors had that really kind of nasty nonlinear, all of them did, output curve. The best way is to use the Steinhart-Hart relation, which is this equation right here. You get all of these constants from the data sheet for the thermistor. A lot of manufacturers, if it's a Ptc thermistor, you will get all those in the data sheet. If it's an Ntc, negative temperature coefficient thermistor, most of the time you will just get a B and then use that simplified B value equation, or sometimes you'll see it written as beta. And you can compute the temperature pretty easily just by plugging in. So you've got the resistance of your thermistor, the resistance at 25 degrees, which is specified in the data sheet, and the B value. You just plug and chug. You can get to the millikelvin level with thermistors if you're careful. If you do all the wiring right, if you balance the bridge correctly, maybe do a little bit of signal amplification, it's no problem to get down into the millikelvin range for resolution. Okay, displacement. There's a bunch of ways to measure displacement. I'm going to do just the common ones that we generally use in the lab, but of course you can use ultrasonic sensors, you can use linear encoders. This is what the machines in the machine shop where they have those digital displays of where they are that are down to about 1/1000th resolution. Those are linear encoders. Linear potentiometers, and DC-DTs or LVDTs. So we'll mostly focus on DC-DTs and LVDTs. That's what we use in the lab. They're relatively inexpensive. I say relatively because each sensor is $700 to $1,000 generally. So take that how you will, what you think about how expensive transducers are. But they're this, it's a differential transformer. So it stands for direct current differential transformer or linearly variable differential transformer. And the idea is we have this core that can slide through the assembly. That's what we're measuring the displacement of. And in the outer part of the transducer, there are 2 windings. It's a transformer. There's a primary winding in the center and secondary windings on either side. As we move that core through, we can change the output of the transducer like this. So let's say that we're in the center. That primary winding, we're feeding an AC signal into. So it's generally a sine wave. For most transducers, it's 10, 15 kilohertz, somewhere in there. That also limits how fast the sensor can respond, its response time. The core's in the center, so we have this alternating magnetic field that we're generating with the primary winding. And the core is coupling that, it's a very ferrous core, couples that to the secondary windings equally when you're in the exact center. Let's say we move the core further into the transducer, further to the left in this picture. Now it's going to couple that energy more strongly into S1 instead of into S2, the two secondary windings. If we move it to the right, now we're primarily coupling into S2. So this is what that looks like if we were to look at the output of the transducer. So this is all the way to the left, all the way to the right, and the null. If you were to hook a voltmeter up across the secondary windings, you would see this symmetric V-shaped curve. Notice how out here it's not linear, and that's because it's beyond the end of the range. We're not going to use that. So stay away from the ends of the transducer again. We've got this two very nice lines here, and then a little bit of offset, possibly. Now, the way you know where you are, which side of the null point you're on, whether you're further in or further out than null, is by looking at the phase of the output. So is it in phase or out of phase with the signal that you're driving the primary winding with? Luckily, most of these transducers have the electronics integrated and give you a nice DC output that goes from negative some voltage up to positive some voltage. So you don't have to worry about measuring the phase and measuring the output and then go ahead and calculating where you are. So to the user, it just looks like minus V to plus V. That varies linearly with displacement. This is what that would look like if you cut into one of them. You've got the windings down here, and then generally on the back end of the transducer, there's a small PCB that has a microcontroller that generates the high frequency that we drive it with, and that then takes the phase and the magnitude of the output and creates a DC voltage out from that. So has anybody plugged these in and heard them whine? Like heard that really high pitch ring? So that's the frequency that you're driving it with. And maybe these, either there's some ringing in the capacitors in here, or if it's a very old transducer, you could even have some loose windings in the coil that are going back and forth. Another kind of displacement sensor is a capacitive displacement sensor. Remember, we talked about capacitors, and we said that anytime you have two conductors that are separated by some dielectric, it creates a capacitor that can store energy. So this works on the principle of we calculate the capacitance between our sensor and some conductive target that we're looking at, assuming their areas remain the same and that the permittivity of free space remains the same, which we hope it does, then the distance is the only thing that can change the capacitance. So we just measure how the capacitance changes, and that correlates directly to distance. So you can measure position. These have a very good high frequency response, up into the tens of kilohertz. So you can measure vibration if it's relatively low frequency. Or you can even use two of them, and when they're manufacturing steel plates and that kind of thing, and pass it through and measure the thickness of an object. You can actually get absolute distance from these. With a DC-DT, it's pretty much relative, but these will give you absolute distance measurements if you reference it. The capacitive sensor is the highest resolution of any of them that we're going to talk about. They're also relatively expensive. One sensor that has a range of about 6 to 8 millimeters, the sensor plus the signal processing electronics are about $5,000. So they're not cheap. They're much more expensive than DC-DTs. Eddy current sensors are cheaper than capacitive sensors. They have about an order of magnitude less resolution. But a capacitive sensor can have tens of nanometers resolution, an eddy current sensor hundreds of nanometers, and DC-DT a micron or so. The way that the eddy current sensors work is we have a big coil in here, we feed it with AC, we create this alternating magnetic field that gets coupled into some conductive surface that we're looking at and generates eddy currents in that surface. These two fields interact, and by measuring the resultant field, we can directly correlate that to the displacement. So again, these are maybe $2,000, $2,500 for one that's comparable to a $4,000 or $5,000 capacitive sensor. So about half the price, but still significantly more expensive than DC-DTs. You can find capacitive and eddy current sensors that are called proximity sensors that don't give you a linearly variable output with where you are in position, but just say, am I close, yes or no? So it's like a switch. You can calibrate it for, say, like homing a 3D printer. That's how a lot of those work now. Okay, pressure. Pressure transducers are a place, again, where a lot of terminology can trip people up. There are absolute pressure transducers, which tell you what the pressure is with respect to a perfect vacuum, ideally. So if we had an absolute pressure transducer right here, and were to project it on the board, it would say 900 and something hectopascals pressure, because that's what the atmospheric pressure here is right now. If we took it to sea level, it should be 101,325 pascals, because that's sea level pressure. The gauge pressure, which is what we deal with a lot of the time, is relative to atmosphere. So if we had a gauge pressure transducer, right now it would say 0, unless you blew on it or something to increase the pressure inside. So it's relative to the atmospheric pressure currently, which that atmospheric pressure can change over time as storms come through and all that. So they're vented, basically. Vacuum transducers are used to measure below atmospheric pressures. It's not common, though it does exist, to have a transducer that can do vacuum and above atmospheric pressure in one transducer. They're generally designed for one or the other, and doing the opposite can damage it. And then differential transducers. A differential transducer has two inputs, and it just tells you what the pressure difference between them is. This is really handy for, say, you have two very high pressure hydraulic lines or something, and you want to know very small differences between them. You just use a differential transducer instead of trying to measure the gauge pressure to a very high resolution. And then there are sealed transducers, which are custom. These are for very specialized applications where they seal a fixed pressure on one side of the transducer, and everything is with respect to that fixed pressure that you specified. And the housings for these vary a lot. There are a lot of manufacturers. I think some people are going to be using sensors like this in their project. Some MEMS sensor, so it's a very small chip scale pressure sensor, like what's in your phone to tell you the barometric pressure, how many flights of stairs you've climbed today. You can generally get about 1 centimeter, maybe 2 centimeters vertical resolution with that kind of sensor, and they're a couple bucks. There are sensors that you could plug into your breadboard, but neither of those are going to fare very well in, let's say, the lab if we want to measure the pressure from some kind of pressure intensifier. So they're these more industrial type enclosures, stainless steel, titanium, etc., that are threaded you can put onto your system. Some of them can even withstand external pressures, like you could submerge them in the ocean or something like that. There's a variety of ways that these work internally. One of the most common is that you've got a diaphragm, and the applied pressure deforms that diaphragm. There's a strain gauge on it, and that tells you can calibrate that to the pressure. Similar, you can have a potentiometer, so a variable resistor, like the one that you used on Thursday, that changes its resistance based on how much the diaphragm is deformed. You can do a capacitance measurement, so a capacitive distance sensor with pressure applied to one side. Or it can actually be the differential transformer setup, like the LVDT. It's just measure, so you're all of these measuring the deformation of a diaphragm. A diaphragm is generally made from some very resilient corrosion-resistant material, so these are not cheap generally. $700 to $1,000 would be a pretty standard figure for a run-of-the-mill transducer. Okay, strain. Strain gauges are what some of you are using in your projects, and I would say one of the maybe more misunderstood of the sensing families. So a strain gauge, if anybody hasn't seen them, looks like this. It's a bonded strain gauge. Blown up, there's these little conductive traces that snake back and forth, two pads for you to solder onto that are tiny generally and kind of a pain to use. But we can measure extension or compression of the gauge down to below the microstrain level pretty easily. This works based on the formula for resistance of a material. So let's say we've got some chunk of, this could be copper, it could be carbon, whatever, between two plates. The resistance of that, let's say it's a resistor that we're stripping apart a resistor, is going to be the conductivity or the resistivity of the material, it's rho here, the length of the material that we're conducting through, and the area of contact on the ends. So what we're going to change is that cross-sectional area in a strain gauge. That works like this. Let's say this is the strain gauge that you stuck to your piece of rock or your piece of metal, and it's at rest. It's no strain, external strain. Now, if we put this in tension, these little pieces of copper have to stretch out because they're being pulled apart. That means their cross-sectional area is going to be reduced, which makes the resistance go up. So as you stretch it, the resistance becomes higher. In compression, you can see that the copper is being compressed, bunched up, the cross-sectional area gets larger, and the resistance goes down. Does that follow to everybody? Yeah. So strain gauges are most sensitive in this direction. Perpendicular to that, they're not very sensitive at all, because the only bits of copper that you're changing the cross-sectional area over these bends, which are very small. So perpendicular to that, they're not very sensitive, just a tiny bit. Most of the time, we deal with a Wheatstone Bridge in some variety, circuit that we've seen earlier, one that you're going to build next week, where there are 4 resistances. We excite it with some voltage, and then we're measuring a voltage differential inside. This is the formula for the excitation voltage. You know all the resistances. That tells you the voltage that you're going to measure out. So you're generally going to solve that for some combination of the resistances R1 through R4.
So is that 2 or R2 in the equation?
That should be R2, yeah. Then there's something every strain gauge is going to have on the package called the gauge factor. The gauge factor is the relative change in resistance, so delta R over the at-rest resistance, divided by strain. Excuse me. That tells you how sensitive the strain gauge is going to be. And it'll plug into all the formulas that we're going to use to calculate strain. A classic exercise with strain gauges for engineering students is you take a Coke can, you put strain gauges on it, you shake it up, and then you pop the top. And now back calculate what the pressure was inside the Coke can. So it's a pretty standard exercise. The quarter bridge means that we've got 3 fixed resistances and 1 strain gauge that we're going to strain. So this is the only gauge that is changing. These could just be precision fixed resistors. It is not incredibly sensitive, but it's cheap because we're only using 1 strain gauge. And they are definitely not free. They're relatively pricey if you buy them new. In a half bridge, we use 2 strain gauges that have an opposite sign. So for example, let's say we're bending this piece of metal. You can put a gauge on the bottom that's in compression and a gauge on top that's in tension. And for free, you get greater sensitivity, greater output voltage variation for the same amount of strain. You can see the equation there if you need it. But the full bridge is the most sensitive arrangement. So notice that this denominator has kept going down and down, and now it's just gone. This is the most sensitive arrangement that you can have. You've got 2 gauges that change in one sign, minus delta R, 2 gauges that change in the other sign, plus delta R. This is what we use on load cells and things in the laboratory. This table is just there for your reference to look at. It tells you if you want to measure, say, axial strain or bending strain or anything like that, the kind of bridges that you can use. The temperature does change. So let's say that you have 1 gauge on your Coke can, and then you heat up the Coke, or you heat up the environment, sorry. The gauge factor, or the delta R over R, will change somewhat. The most common way to get around this is to use a dummy gauge. So the dummy gauge is in a direction that we're not measuring the strain. If you can't do that on your physical object, sometimes you have a dummy gauge sitting on the exact same material very close by, and use it to remove the effective temperature entirely. So it's a static, known gauge. So any change in resistance due to temperature it has, this will experience as well, and they're going to cancel out when you have it in a bridge configuration. And mostly when you apply strain gauges, it ends up with very careful wiring, magnifying glasses, and steady hands, because they're small and you have to get pretty creative sometimes with where you can tuck all the wire away. Okay, so this is going to be homework, but it's not going to take you more than about 5 to 10 minutes probably. On the website, there's a Thermistor Calculation activity where I've given you some data. I've given you a file that has this vref, what we're driving this divider with, and vout. And this figure's on the website. And I've told you the part number of this thermistor and given you the data sheet. So you're going to go to the data sheet, look up what the B value is, what the R25 value is, and then calculate what the time series of temperature was. I'm going to tell you this was an experiment that was done at room temperature. I think it says this on the website. So if you're getting hundreds of degrees Celsius or minus hundreds of degrees Celsius, it's not right. So you should be getting answers that are close to room temperature. So that'll be due Thursday. Like I said, should just take you a couple minutes. The other thing, we'll do this on Tuesday, is find something to put strain gauges on, because that's going to be the lab on Tuesday. I did this several years ago. I put strain gauges on a coffee cup, and you could pour coffee in it or hot water and measure the thermal expansion of the ceramic, and then measure the coffee cooling down afterwards. So it could be a piece of rock, it could be a piece of metal, it could be a Coke can, whatever you want. But bring an object. It needs to be semi-smooth. You know, if you got a really bumpy surface, we can't plaster the strain gauge down to it nice and cleanly. All right? Okay, see you Thursday.
Anyone who didn't get the